All right, guys, we're going to solve some systems of equations by graphing today. So I love starting off solving systems with graphing because I love how it provides that visual component so we can visualize what's going on and the types of solutions that we might find when we are solving algebraically later on. So before we get started, we got to think, what in the world even is a system? I thought we were just solving singular equations. What is going on now? So, a system of linear equations is a set of two or more. In this case, we're just working with linear equations. As we learn more, we'll be able to solve systems that involve multiple kinds of equations with the same variables. Now, this is important. They're just going to be x and y, but we can't have, say, one that's in x and y and one that's in y and z because we would not be able to use them to solve for all three of those different variables. Now, when I say solve for, what is it we're looking for? So a solution to a system is a point, right, an ordered pair, x comma y, that makes both equations in the system true. So what I mean by that is, how can if I get this point, x comma y, and I plug it in to the first equation, I'll get out a true statement. And if I plug in the second equation, I'll also get out a true statement. So let's see what that looks like here in example 1. So we want to know, is this point 2 comma 1 a solution to the following systems? So I'm going to go ahead and in these equations where x and y are, I'm going to plug in that point. So first, I like to kind of label these equations 1 and equation 2 so that I can keep them straight in my brain. And I'm going to leave little placeholders where x and y were and a little question mark over that equal sign because I'm not sure if these are going to end up being equivalent or not. Now I'm going to go in and plug in this 2 comma 1. And I like to use different colors here so that I can visualize when I'm looking back over my notes later. This green ordered pair is what I plugged in. All right, so let's go ahead and start simplifying. So if I carry out that multiplication, my 4 plus 1, I'm hoping that's equal to 4, but oh no, we've got 5 equal to 4. Well, that's not true. So I can actually stop here since I know it doesn't work for this equation. It doesn't matter if it works for the other one. It cannot be a solution to our system. But since we went ahead and word it out, I might as well carry on. And see, that one didn't work either. So 5 is not equal to 4, and it's not equal to 10. So, both of those are not true. And so therefore, this guy, 2 comma 1, he's not a solution to this system. All right, well, same ordered pair, but we want to see now if it works for this system over here. So again, I'm just kind of leaving blanks where I had everything before and those question marks just in case, right? Because we don't know if this is going to be equivalent yet. I'm going to plug in 2 and 1. All right, so over here, this is going to become 2 plus 2. And we know that's 4. And this is 3 equals 3. Remember, we had to check both. I had to make both of these guys work. But because it worked for both of these equations, that's when we're able to say that this guy, 2 comma 3 here, or 2 comma 1, sorry, is a solution to our system because it worked for both equations. So now that we've kind of wrapped our heads around the vocabulary, right? What's a system? What does it mean for something to be a solution to the system? Let's go ahead and see what we can do here with graphing. So, steps that we're going to follow to solve this system of equations by graphing. Well, first things first, we're going to make sure both of our equations are in slope-intercept form. Oh, scribblings. Slope-intercept form. Now we can graph from other forms, right? I can show you how to graph from standard form and from point slope form, but slope-intercept form, if they're both in slope-intercept form, it just makes life a little bit easier because then we only have to think about one method of graphing instead of having to use multiple. Then we are going to graph, right? If it says solve by graphing, we know we got to graph our equations. And so since they're in slope-intercept form, right, we're going to plot the y-intercept. And then we're going to plot more points using the slope. Then we're going to locate that point of intersection where the two lines cross. Then, if we've got time, right, if this is a test or quiz, we're going to check the solution in both of our equations. Okay, so let's go ahead. I'm going to call this guy equation 1 and this guy equation 2, just because it helps me keep everything straight here. And both of these are in the standard form. So we can get slope-intercept form by first subtracting x from both sides. This first one. And then dividing both sides by 2. So we get y is equal to negative a half x plus 2. And then this next one, I'm actually going to graph in green. So here I only need to subtract x. I'll end up with y is equal to negative x plus 3. And now got my two equations that I can graph. So I'm going to start with equation number 1. So y-intercept at 2 and a slope of negative a half, which means it's going to go down 1, right 2. Then use the slope to plot more points there. Then I'll connect them. And see, here's where using your graphing calculator might be advantageous because even though I plotted great points here, I drew a really bad line, right? Very imprecise. So not a problem at all. Just erase. Try again. Alright. Always putting arrows to signify that line is going on forever. Alright, now this guy, this y-intercept at 3 and a slope of negative 1. Connect those dots. And as you can see, they cross right here. And that point is 2, 1. So you might be like, hey, this all sounds familiar. Well, we actually already checked our work, right? We checked our work in example 1. I gave you this problem with the solution already. We already checked it. On to the back. Couple more examples. All right. I want you to go ahead and try this guy on your own. So you can go ahead and try this out. Pause the video. and then come back and see how I get this one done. So go ahead, pause. All right, welcome back. Let's go over how we graphed these guys. So first things first, I noticed that these worked in slope-intercept form. So I'm going to go ahead and rewrite them. So I gotta subtract 2x from both sides here. I'll have 3y is negative 2x. Oops, getting ahead of myself there. Plus 9. Then now I can divide everything by 3. Now if y is negative 2/3 x plus 3. Alright, and then over here, our second one, we only have to subtract 2x, and we'll end up with y is equal to negative 2x plus 3. Alright, so I'm going to graph the blue one first. So y-intercept at 3. And then a slope of negative 2/3. So it goes down 2 over 3, down 2 over 3. We'll end up somewhere kind of a little bit off the graph there. And here, I'll go ahead and connect those dots. Okay. Always putting arrows at the end. And then next, also has this y-intercept of 3, and this has a slope of negative 2. So it's going to go down 2 over 1, like so. And then I'm going to connect those dots. Alright, and so we can see here our y-intercepts. You may have been able to tell that already just from this step, but our y-intercept there at 0, 3 is how we go about checking this. Or our solution is. Now let's talk about how we go about checking this. So I'm going to use my note-taking superpower. I'm going to shrink this down here, maybe. No? Jeez Louise. Alright, so I'm just going to move this over here. So that I have more room to graph it. Or to check my work, excuse me. So when I'm checking my work, we're going to want to check it in the first one. So 2 plus 3, hopefully that's equal to 9. And then 2 plus whatever y is, hopefully that's equal to 3. Now I'm just going to plug in, use black I guess, 0 for x, 3 for y. This one will come out to be, this cancels, this cancels. This is 9 is 9, 3 is 3, and we are good to go. So we know that 3, that y-intercept of 3, or 0, 3, that is our solution. Alrighty. And the next 2 examples are 2 of my favorites because there are actually 2 other things that can happen, cool things that can happen when we are graphing, solving systems in general, but I think the graph really helps us understand what's going on here. So if we look at example 4, same thing as usual, right? These guys, not in slope-intercept form. So we gotta fix that. So just rewriting the first one down here. Let us solve. Divided by 2, yeah, y equals negative 3/2 x plus 5. I always tell students, especially when dealing with slope, fractions are our friends because fractions make slope so easy to work with because it tells you in the numerator, right, your vertical change, and in the denominator, your horizontal change. And with decimals, right, I don't know how to work with that. I'd have to convert it to a fraction to be able to even think about what's going on. So fractions, so nice. Fractions are our friends. Alright, so we're gonna subtract 6x from both sides here. We're gonna end up with minus 6x plus 12 and divide everything by 4. So 6 and 4 both have a factor of 2 in common. So if I divide both those by 2, we'll get negative 3/2 x. And 12 divided by 4 is 3. Alright, so let's go ahead and plot these. I already got my green ink going, so why not start with that guy? He's got a y-intercept here at 3, and a slope of negative 3/2. So he goes down 3 over 2, down 3 over 2. Alright. Alright, so there's that guy. Then I'll grab the first one. He starts at 5, or not starts at, but he's a y-intercept at 5. Whoopsies. And same slope. Oh, interesting. So we're going down 3 over 2. That's interesting that they have the same slope because we know that these guys, because of having that same slope here, these guys are parallel lines. Oh my goodness, that was embarrassing. I second guessed myself there. Don't do that. Alright, parallel lines. And we know about parallel lines that they never intersect. So maybe you, at this stage in the game, already saw that when you set these equal, and you didn't even have to graph. But that's okay if you didn't notice. You're just focused on the task at hand. So these guys, they're never, ever, ever going to cross over. So we say that there's no solution because no point out there in the coordinate plane exists. It's going to make both of those equations true. It's just pretty cool. We think about all the numbers out there. It's not a single order pair. That's going to work for the system. Pretty cool. But we can have the opposite problem too. So let's see what that looks like here in example 5. So in example 5, I have the following. So starting off business as usual. Gonna rewrite all of these. And you'll notice I didn't put a single one in the notes in slope intercept form. Probably because I'm an algebra teacher and I want to practice rewriting here a linear equation, so that's okay. So I'm going to subtract 2x here. Ooh, and I got negative y equals negative 2x plus 3. And multiply or divide, doesn't matter, both sides by negative 1. Yeah, end up with y is equal to 2x minus 3. Don't forget, he gets negated as well. Over here, I subtract 4x from both sides. I have negative 2y is equal to negative 4x plus 6. And then I'm going to divide both sides by negative 2. I'll get y is equal to 2x plus 3. Oh no, look what I did. I didn't follow my advice from earlier. I forgot to negate that 3. Oh, that's better. There we go. All right, so now I've got, oh boy, what do you notice here? Well, if I graph that first one, it's y intercept, oh my goodness, -3, a slope of 2. All right, so there's that one. And my other equation, they didn't start out looking the same, but right, like these guys in here in the system, they don't look the same, but they ended up being the same line. So I didn't draw my line very well there. But this is where I think taking notes in color comes really in handy, because notice how I can see that I plotted the blue one and I plotted the green one, but really what ended up happening is they're the same line. So this is what's called um, coinciding, right? They are in line together, coinciding lines. Really, it's the same, right? They're the same. So what ended up happening, if we look up here, is this equation right here, this equation number 2 is a multiple of the top equation. So if I took that top equation, multiplied it by 2, that's how I get the bottom equation, which is why they looked different. They end up being the same line. And so what that means is that every single point on the blue line exists on the green line and vice versa. And so this, rather than having no solutions, has the opposite problem, where this has infinitely many solutions. Oh my goodness. How many times can I misspell for you guys today? Ah! Alright. Infinitely many solutions. And there you have it. So we have seen an example here of a system having infinitely many solutions. We have a system here with no solution, and we've seen systems that had one solution. So if you like to write little summaries to yourself, right, here at the tippy top, right, so when graphing, right, one thing we learned today is that systems can have no solution, systems can have one solution, or infinitely many solutions. All right, well, I hope you have a great day.